Human scale quantum superposition. 1. R. G. Unanian, B. W. Shaw and K. Bergman Phys. Reverend Let. 99, 100401, 2007. A. A. Clark, S. M. Gervin, and A. D. Stone, Phys. Reverend Let. 99, 1636012007. 2. T. Cato, Lectures on Differential and Integral Equations, Princeton University Press, 1947. 3. http://web.amath.unc.edu/math.n/notes/nmr.pdf submitted by Rashid Unanian, Physics, Clemson University. http://www.clemson.edu/rashid/index.html. I've taken a moment to read the paper mentioned below, and I am a bit confused if the authors have in fact proved what they claim. Let me see if I can summarize their main theorem. A. My impression as a mathematician physics reader is that they haven't proved their claims in any rigorously mathematical sense. That is, even if you are extremely permissive as to the definition of the word proof, as in, we have shown that there is no proof of, you can look through their claims and see that you expect mathematical rigor in one way or another. One way to think about it is to consider the meaning of certain terms. In quantum mechanics, wave function is synonymous with a function from real or complex numbers to complex numbers. So, in their statement about wave functions, the author says they are normalized as is usual in quantum mechanics. One way to read this is to say that they were thinking the state is the wave function. So, when they say in a final theorem, the probability interpretation of such states is zero, they are already using the normal quantum mechanics definition, hence the word interpretation in the passage cannot mean what they are claiming. Similarly, if one reads them literally, that would mean that the probability density in any location $\vec r in an arbitrary complex valued wave function $\psi\vec r is zero because one can add this zero to this probability density into the same wave function with the opposite sign of imaginary component, therefore cancelling the two. $1 \psi $2 \psi\vec r \psi \vert \psi imaginary component \right equals $0 but this means that there are wave functions that are constant i.e0 in all points. This is not true of wave functions that are normalizable. For a normalizable state, it is possible for there to be an arbitrary complex valued function whose density in a point $\vec r is zero. The author's claims in the paper are not as ridiculous as they might look upon first glance. Rather, the claims are in the spirit of something already shown in a paper by R. P. Feynman and J. R. Schmidt using their famous path integral formulation of quantum mechanics. At that point of history, they had no definition of quantum mechanics on any mathematical level, at least in their approach. They showed that a state that was non-normalizable, i.e. of infinite norm, is necessarily stationary. So, they really did show one type of proof to such a statement, since a state with infinite norm would always be at its stationary point. What they have shown that the probability density is zero if the wave function is not normalizable, i.e. the wave function is not square integrable. They have not proven that the probability density goes to zero for wave functions that have zero normalization. Of course, in their paper they have only claimed this in the final paragraph. Even with their claims in that paragraph, it seems reasonable that there is a lot of work to be done for their claim in their results section to be mathematically rigorous. Even when this is done, I'm still confused as why then a non-normalizable state cannot be mixed. One can think of it like this. Given any wave function $\psi\vec r that is not normalizable, one can mix it with a normalized constant state by adding a state with $0 amplitude anywhere. So, in this case of a non-normalizable function $\psi\vec r then what is the point of being able to mix it with another? Consider $\psi\vec r equals $\psi\vec r plus backslash delta underscore backslash vec r.